talk to you today about various approaches that could be used for transferring patterns onto the wafer for building various microsystems. You have seen this slide about the process flow required in building most microsystems. You have seen in a previous lecture the various deposition schemes that are required for the depositing thin films onto this wafer. So, in today's lecture we focus on how resist could be put on these wafers and how patterns could be transferred and onto the thin films and some of the required relevant steps in this context. Thin films used in MEMS include thermal oxide of silicon, various dielectric materials. These include polymeric materials, ceramic materials, as well as silicon compounds such as silicon nitride and silicon dioxide. You will also come across polycrystalline silicon, which is usually known as polysilicon. This is a very good contact material. It is also used in the context of microsystems as a structural material. You will also require several metallic films such as aluminum or gold for conductors required in the processing of microsystems. Active materials, smart materials such as ferroelectrics and piezoelectrics are also used in building smart microsystems. These thin films can have typically multiple roles, and one of the common examples is the polycrystalline silicon. As I mentioned, this could be used either as a contact electrode or as a structural member for microsystems. So, these thin films can have these multiple roles, but these roles can be defined only when the thin film is patterned into something. Otherwise, the film is sitting all over the surface. So, it is only adding bulk to the surface of the wafer. So, patterning of these thin films is essential to build devices, to build microsystems on a wafer. So, to selectively remove these thin films to form such electrodes, dielectric layers or insulating layers or microstructures, we need to transfer a pattern or create a pattern on the film on the surface of the wafer. So, it is also sometimes required to create doped regions of various semiconductor materials or layers on the wafer. This is usually done by diffusion and ion implantation, which is usually done after creating a masked film layer which is patterned. And so, in today's lecture we will talk about all these in the context of building microsystems. As you may have seen in previous other lectures, commonly used metals in the processing of microsystems include aluminum, which is, as I mentioned, and there is a very simple simple material to be deposited very effectively onto silicon based surfaces. Another common example is gold, which usually require a sublayer before that. Usually chromium or titanium is used for that purpose. You also come across platinum and palladium in several sensing applications because of their special characteristics. You also have various forms of silicon dioxide used in the context of microsystems. It also come in the form of glasses, and these are also used in microsystems. Another silicon based compound is silicon nitride, which could be deposited by LPCVD or PECVD techniques and has very interesting properties for building microsystems. Another silicon based film is known as polycrystalline silicon, which consists of small crystallites of silicon. So, within the crystallite it is a crystal of silicon, but between crystallites there are grain boundaries, because of which it is not a single crystal structure, it is a polycrystalline structure of silicon, and still it has very good characteristics that are similar to that of single crystal silicon, especially from the mechanical point of or properties point of view, and hence polycrystalline silicon is also widely used for microsystems. Polymeric materials used in microsystems include photoresist acinides and other polymers such as PMMA and polymethyl acrylate. And one of the materials that is becoming fast popular in the context of microsystems is SU8, which can be used for a wide range of thickness of up to millimeter thickness, and hence it is used when one need thick structural members or for thick resist materials and molds and other microstructure applications. So, there are a wide range of applications possible for SU8 in building microsystems. Now, let us look at how these can be patterned. One of the very popular technique is known as lithography, which is usually based on visible light, and hence it is called photolithography. We use a UV beam for the processing, for the exposure in this particular context. There is a variant, I would say, of the approach, with some significant changes in the process steps required to, and is called Liftoff process, and we will describe this a little later in this lecture program. There are also other advanced techniques based on electron beam or an X-ray for specialized applications, especially for high precision geometries to be patterned. Lithography is a very common process for building printed circuit boards. In this case, if you have seen a printed circuit board, a bare printed circuit board, it is essentially a copper clad dielectric material. And what is usually done there is that this copper clad material is coated with some kind of a resist material, and then this resist material is exposed after it is cured, is exposed with a mask film, so that certain regions of this is exposed, whereas the other regions which are hidden by the mask are not exposed to the UV light, and then the resist film is then developed, which would essentially create hollow spaces through which the copper on the printed circuit board is etched, so that we can have traces on the printed circuit board. What we need to do to build microsystems, to pattern microsystems, is something similar. So, the first thing that we need to have is a mask. A mask is essentially a stencil used to repeatedly generate the desired pattern of resist pattern, which is transfer them onto the resist coated wafers. It consists of the mask used in microsystems. Unlike in the case of printed circuit board, where typically a film is used, here it consists of a flat glass or quartz plate coated with chromium or similar material. And then this is patterned and kept as the stencil for reproducing several devices or several layers with the same pattern. So, creation of mask is also critical, and these are usually done by a 1:1 transfer of an image, which is first created using a CAD tool. Typically, people use what's commercial software known as L-Edit, and several laser based plotting or writing schemes are available for transferring patterns onto the mask. One of the laser writer is based on a solid state laser source at 405 nanometer wavelength, which can have feature sizes up to 1 to 2 micrometer, as low as 1 to 2 micrometer, and it can typically take various forms of drawing files, and has extended capability in terms of multiple layers and gray level, and this can even be used to transfer the pattern directly onto the wafer as well, not necessarily always to the wafer or always to the mask itself, and both direct writing option as well as mask writing options are possible with today's laser writers. So, several materials could be patterned, not just the common photoresist using these laser writers of today. One example of a laser writer available with the facility in my institute is shown in this picture here. The resist material that is used in microsystem fabrication is also slightly different from what is used in the printed circuit board fabrication. This, as in the other case, is polymer based resin, which essentially changes its structure when exposed to the particular UV light, and it consists of the sensitizer and the solvent as in the other case, and we can get positive and negative tone resist materials commercially and could be used for the fabrication of microsystems. The difference between the positive and negative photoresist is illustrated in the schematic here. Let us say that we have a pattern like this on the mask plate and is being transferred onto the wafer. After it is transferred, when you have a positive resist, you get exactly the same, and when you have a negative resist, you have the opposite of that transferred onto the resist layer. There are some differences in the way these resist materials could be used, and that is obviously why both these types are available. uh, if there are some dirt on the mask plate, that would result in what are called pinholes in the negative when we use negative photoresist, whereas the chances of forming pinholes is almost negligible and almost never possible in the case of photoresist. On the other hand, for positive photoresist is typically more expensive. Positive resists are usually used when better precision with lower feature size are required. The step coverage in positive resists are usually better than negative photoresist. There are several examples of positive and negative photoresist materials that are used in typical laboratory environments. Now, let us see how photolithography could be used for the fabrication of a microsystem, in this particular case for patterning a thin film layer. What we show here is patterning an outside layer on a silicon wafer. So, what we need to do first is obviously to form this outside layer on the silicon surface. This, as I mentioned in another lecture on formation of thin films, this could be done by dry or wet oxidation. It is also possible to have SiO2 films, silicon dioxide films on silicon surface by various other deposition schemes such as LPCVD. So, let us say that we have a silicon wafer and it is, let us say, oxidized to form this outside thin film. To transfer the pattern, as in the case of printed circuit board example that I cited earlier, the first step required is to coat a resist, and this is done by spin coating. In spin coating, what we do is we put a few drops of the resist material appropriate on the surface and hold it on to this vacuum chuck in a spinner and spin the wafer at several thousand RPM. After it is spun, what you get is a uniform thickness of the resist on this surface. It is then taken for a what is known as a soft baking, which is usually done by putting this in a oven or a hot plate at about 80 degrees centigrade for about 10 minutes. After that, it is exposed to the UV beam by with putting the mask on top of this. Usually the mask is placed directly on top of this, so that there is little diffraction happening, chances of diffraction at the edges of the mask. But it also has a issue that sometimes the debris from the resist can get attached to it and the mask plate by itself may get contaminated, but usually it is done at not at this kind of a distance, it is done closely to the surface. After it is exposed, this film is developed by inserting it in a bath, and when you are developing, the unexposed region of the resist goes away. So, what we have is a clear window through which we can essentially etch the film of the outside, but not quite yet, because the resist material that is here may not stand the chemical reaction, the reagent that you will be using. So, to do that, we again heat it so that it sticks well to the surface, so, and it does not go away when it is exposed to, let us say, the acidic reagents that are required for etching the silicon dioxide. So, when it is kept in this wet bath, it is you can etch the silicon dioxide, and after that we can strip the resist by etching and various methods. So, what we get finally is a thin layer of silicon dioxide, which was deposited by various approaches including oxidation, but patterned by the lithography kind of thing. So, as you could see from here, there are several important things that are important steps to be followed for patterning any of these materials, including metallic films on the wafer surface. To transfer the pattern accurately onto the wafer surface, we use what is known as a mask aligner. In a mask aligner, we can accurately position the mask plate over the wafer. You may ask, why is it critical? In a typical process flow of building a microsystem or an IC, we need to register where the reference points are, so that the subsequent layers one over the other are aligned with respect to some known references. So, it is possible to do that by accurately positioning the mask plate above the wafer. So, we intentionally create alignment marks in every layer and every processing layer, and these are required to be carried through till the end of the processing, so that proper alignment would be possible. So, in this particular case, what you see is a double sided aligner, in which case you can see it from two directions, from the top and bottom, and that is also important in the context of building microsystems. In microsystems, we as you may see, you may want to process some part of the device on, let us say, the top surface of the wafer and some part in the bottom surface. So, an alignment between the top surface to the bottom surface is also important, and that can be done using a what is called a double sided aligner. To etch the thin films, you have seen silicon dioxide in the previous example, where one could use buffered HF. When you use silicon nitride, various concentrations of HF or even phosphoric acid could be used. It is the etch rates do depend on various properties and how the film is actually deposited. You may also want to pattern various metals, and different compounds are used for etching them. As I mentioned, the lithography used in microsystems is similar to what is done in printed circuit board fabrication, but in printed circuit board fabrication we usually get an accuracy of about 2 mils, which is about 50 microns. Whereas, as I have mentioned earlier, it is possible to get about 1 to 2 micron in a typical lithography process used for building microsystems. This is done based on by extending the lithography technique by accurately controlling various parameters used in the exposure, as well as in creating the thin film of the resist and things like that. One of the key parameters that affect the resolution in building, in transferring pattern, is the diffraction. As I mentioned, it depends on the separation. Its effect will depend on the separation, but it primarily depends on the wavelength. So, when you really want high resolution structures, you may want to use lower wavelength beams. It's the thickness and the proper positioning is also critical in terms of controlling and repeating the production of the various patterned layers. You will also come across extreme UV lithography because of these reasons, when one would want to stretch the limits of lithography. There are several new generation techniques used in lithography for high resolution geometries, not so much in the context of microsystems, but usually in the context of sub micrometer technologies for CMOS. It is also possible to use electron beams for patterning layers in these applications. Even ion beams could be used for this purpose. What you see here is an example of an e-beam lithography in our facility for patterning very small dimension geometries in such as dots of several tens of nanometers or lines of few nanometers width, and this is possible by using PMMA resist and using exposure using an electron beam approach rather than the UV light, as you see in the previous examples. So, the process steps are somewhat similar. You spin coat the PMMA resist, and then the sample is loaded onto the equipment, and the patterns are transferred using e-beam lithography, and then it is developed and etched. So, it has various applications. The e-beam lithography has applications in nanolithography up to and even lower than 20 nanometer resolution, and it has significant applications in photonics, because these dimensions come close to the wavelengths that could be used and the gratings that could be created for various optical devices. It is also possible to extend these for 3-dimensional structures for microsystems applications or for CMOS applications. Some of these equipment available for the e-beam lithography can also be used for nano probing and high resolution SEM inspection of the layers that are formed. Liftoff technique is another pattern transfer approach which is somewhat similar yet different from the lithography approach. In a standard lithography approach, what we do is first deposit the thin film and then coat it with the resist and then expose and develop, and after that you remove the unwanted material. Whereas in Liftoff, what is usually done is you first coat the resist and then transfer the pattern by UV exposure, and after that deposit the thin film. Usually metal thin films such as gold are patterned by using Liftoff technique. As you may know, for etching gold usually aqua regia is used, which is a nasty chemical. There are other chemicals that could be used, but still it is usually preferred to go with the Liftoff approach for the patterning of accurate patterning of films such as gold. So, when the resist is removed, the unwanted metal will go, and we will see that soon. So, with Liftoff technique, we can get high resolution geometries patterned, and as I mentioned, it is typically used for gold layers. So, as in the previous example of photolithography, the objective in Liftoff is also the same. It is to pattern a thin film layer, and in this example we look at how to have a patterned layer of gold formed by the Liftoff technique. We start with the silicon wafer. The next step is not the deposition of gold, because that is what you do if you are doing photolithography. In the case of Liftoff, what we need to do is basically to coat the resist. But what we normally see in practice is that the gold does not adhere well with the silicon, and in many practical applications you do not actually put gold onto the silicon. So, in this particular example we have a wafer which is actually oxidized or coated with a thin layer of oxide before the resist is formed, and this is not what is to be patterned. This is put essentially for other reasons. So, then we put the resist first and then soft bake it and then expose it, and then we develop that resist, and you do not necessarily have to do the hard baking. What we do next is the gold deposition. Now, if the resist coating is substantially thick and the coating scheme used for the gold does not have the step coverage, what you can see is that there is a gap between this. So, now if we put it in a solvent in which this resist can be dissolved, as the resist goes away, along with that the metal on top of it will also go away. So, what remains there is a patterned layer of gold. So, as you could see, the sequence of events are slightly changed in the for processing for pattern transfer by Liftoff. And what you have avoided in this particular case is etching of the target of the gold layer. If you were to do the same thing by lithography, after the pattern transfer we would be doing the etching of the gold. That would have required aqua regia and other chemicals such as iodine, for example, but in this case that is avoided. But what is critical in this case is to have the a step coverage, so that there is no continuity between these gold layers, and possibly a good thickness of the resist can ensure that. But we can't just keep on increasing the thickness of the resist, because if you have it too thick, it may not uh, develop well, it may not expose well when you use a normal UV light. So, we need to have some kind of a compromise between the thickness and the coverage. There are some innovative schemes which could be used, so that there is a discontinuity, we can ensure that there is a discontinuity between these films, so that the final removal by dissolving the resist material would result in removal of the unwanted metal and not the metal that you would need to keep over there. So, the Liftoff technique in fact can be used for various materials, including metals and dielectrics. So, in Liftoff we can have very fine resolution features by wet chemical processes. What is critical, as I mentioned, is that the dummy layer, the photoresist layer that you are using, should have an undercut profile after development, so that there will be a discontinuity between the top and bottom metal layers. There are several approaches, as you have seen here, the pattern transfer is done or similar to what is done in the case of lithography. It is also possible to use the direct writing option, as I mentioned earlier, for this purpose, which is essentially a maskless approach. We are directly writing onto the surface of the wafer. So, in this case, because the exposure characteristics, certain precautions have to be taken to ensure good step coverage, so that there is a discontinuity between the films that would be formed. To do that, one of the approaches that has been developed in our center is based on modifying the resist material, and it is called an image reversal process. In this case, after when it is baked after the exposure, some compounds are formed on the surface which would enable the undercut. So, as you would see here, what we do is that onto the wafer we spin coat this modified compound, and then when it is exposed, this salt is formed on the surface, and after that, when you are actually doing the pattern transfer by the laser source, there will be an undercut, and this undercut will help in having a discontinuity between the metal film on the top and the metal film below. So, when the resist material is dissolved in the solvent, the metal film on the top will go away and the one below will not be taken along with it. So, that will stick better with the surface when we follow this modified approach. So, as you see from the flow of events required for building microsystems, pattern transfer could be used here for building these films patterned. It is also required to create doped regions, as I mentioned previously. Doped regions are required for semiconductor devices. It is very commonly known that we would need N and P type regions in any semiconducting device with various doping levels. Diffusion and ion implantation are two approaches used for this purpose. Such diffused or doped regions are also useful as what are known as etch stop layers. An etch stop layer is a region where the chemical reaction characteristic of the surface is different and usually much lower than the remaining. So, when some regions of the surface is doped, it reacts less with the reagent and hence cannot be dissolved as compared to other regions, and that is very useful in building certain geometries on the silicon wafer. Hence, diffusion is an important step in transferring pattern, after transferring pattern in building microsystems. N and P type diffusion, N and P type regions can be formed by depositing either phosphorus or boron material onto the silicon. It is done at extremely high temperatures. In a in our case it is a templess furnace. There are different options available, and you typically have the nitrogen gas as the atmosphere. The dopant by itself is coming from either a compound of phosphorus or silicon, which is essentially the source of the respective materials. In these cases, when we really want to only diffuse onto certain regions of the surface, we obviously do not want to diffuse everywhere. We need to have defined a masking layer, and usually silicon dioxide is used as the masking layer. So, the silicon dioxide is first patterned by the approach that we have seen so far, and then a region of the wafer is diffused with these compounds to diffused in these high temperatures to get the doped regions of the wafer. And the diffusion, as the name indicates, means there is some kind of a diffusing happening over there. What is happening is that from the source of the dopant, first the phosphorus or boron is transferred and sort of deposited onto the surface of the wafer. After that, we do a process typically known as drive-in, which includes some kind of a oxidation or inert gas atmosphere, which helps in redistributing the dopant into the surface of the wafer, into the some depth of the wafer, so that we can have a uniform coverage to certain depth on the wafer. So, these two steps are typically used in process in realizing such uh, uh, diffused regions or doped regions. As you see here is is a pair of operators working with a furnace used for diffusion in the facility here. Can these graphs indicate the process parameters used for phosphorus, and what you see here is the process parameters used for the diffusion of boron. And as I mentioned, both of these are important in various contexts for the fabrication of different doped regions of silicon. So, as you see here, the patterning and the building of microsystems would require a series of such deposition and patterning steps to be repeated. So, as you recall, the various materials are used for building microsystems, and where these material thin film layers are individually patterned one at a time for building microsystems. But still, as you could imagine, lithography is a planar process. This process can only be used for transferring a pattern onto the surface or a film on the surface of the wafer. Now, how do we extend these approaches into building microsystems? So, we will touch upon how this can be done to realize some microstructures, and how these processes that we have seen here could be extended for building microsystems. In this context, it is interesting to note some of the emerging approaches for lithography. There are techniques such as nano imprinting which are emerging for mold, which basically make use of molds made by the e-beam lithography, which, as I mentioned, can result in high resolution geometries, and these molds are essentially reused multiple times so that we can get better resolution geometries at higher throughput. So, the cost of production using e-beam is basically shared because we are reusing the mold. So, this approach by itself become a low cost approach for building microsystems. And in another similar approach is based on what is called stamp lithography or soft lithography, which also basically use an initial mold made by the high resolution approaches and reusing them for productionizing different devices. It is also possible to use a technique known as probe lithography, which essentially use oxidation by arcing for the pattern transfer. In building microsystems, or strictly speaking even nano technology based systems, it is possible to use what is known as self assembly for their overall structure. So, this is essentially a molecular level process and it can be extended for 3-dimensional structures by techniques known as stereolithography. We will talk about some of these in more detail in another lecture, where we talk about polymeric materials and microsystems based on polymeric materials. So, we will see how three-dimensional structures can be patterned on silicon using lithography. The lithography technique, as I mentioned, is essentially a planar technique. We can only use it for patterning the topmost layer, because the beam that is used for exposure is only capable of having only the certain thickness. So, it does not go deep into the structure and only pattern the resist layer in most cases. And in many cases it fails to when you really have deep structures. So, how do we build thick structures, and how do we realize moving structures based on lithography? We still build one layer at a time and pattern one layer at a time, but we can arrange their sequence in such a way that we can remove material below one layer. For example, we can have a dummy layer and create a structural layer above this dummy layer, and later selectively remove this dummy layer to create moving space. You have to remember that when you have multiple thin films, their properties could be different. So, the choice of materials used in these multiple thin films is critical in realizing such structures for microsystems applications. It is also possible to use the windows created by the etching processes that we have seen as the mask, and further on dig into the silicon wafer by etching the silicon wafer. So, we can use such approaches to remove the silicon from the substrate itself selectively, obviously, to build what are known as bulk micromachined structures. There are also approaches based on non-silicon materials such as ceramics and polymers. So, we will now briefly see how these can be done for silicon micromachining. In silicon micromachining, the processes are essentially based on photolithography, and it is used for somewhat three-dimensional structures in complex forms, but essentially lithography, as we have seen, is a planar approach. We need to tweak it to get this three-dimensional approach, three-dimensional structure. Surface micromachining is one of the common approaches, scheme of events required for fabricating such structures. What is done here can be explained based on the process steps that you have seen in deposition and patterning. What we need to do on top of this silicon wafer is to first form a silicon dioxide layer, which is to be patterned to create this hollow space, and then deposit a second layer, which in this case consists of polysilicon, and then make it to freestanding by removing the outside. Polysilicon, as I mentioned, is a good structural material and that can be used for microsystems applications. And this is obviously a structure that is freestanding. Hence, this layer which was deposited second is known as the structural layer. The layer, the dummy layer that was removed is known as the sacrificial layer because it is removed afterwards. So, in the final device you do not see that sacrificial layer, what you see is a freestanding cantilever. So, as you could see, we only need to deposit and pattern and deposit and pattern to form a freestanding cantilever structure. There are several interesting nuances which are very critical in realizing such structures repeatedly. We will see some of these in subsequent lectures when we go deep into surface micromachining and bulk micromachining for the fabrication of microstructures. But as you could see, it is essentially the deposition and patterning of materials, suitable choice of materials and the control of their deposition schemes that is important in building such microsystems. Thank you very much.